Okay, folks, I'm going to record this short video on how we can calculate the diffusion limited rate constant, which occur when activation is not limiting our reaction, or in other words, when the activation energy is small. Our reaction will typically go as fast as diffusion will allow, which, recall, that's the flux of matter due to a concentration gradient. So I'm not going to derive these equations. We're just going to present them and how to calculate them. So there's two different ways you can calculate the diffusion coefficient, and they both lead to very similar results. So what is all this stuff? Well, D, that gives us our diffusion coefficient, which is a measured quantity, and the solute and solvent matter, those are important. So for just a very simple calculation, we'll use the D water coefficient. So in other words, the diffusion coefficient for a water molecule diffusing around other water molecules, right? So that's roughly about 2.3 times 10 to the minus fifth centimeter squared per second. I'm going to keep everything in the centimeter unit so that we can compare things to the cubic centimeter per molecule per second value. So now what is this R star thing? Well, this ends up being the average distance between molecules in a liquid, right? So we just calculated the mean free path for gases. It's much, much different for liquids. And we can basically use the molar mass and density of a liquid, right? This calculates the volume of the liquid and takes the 1/3 power of that to turn it into a distance. So again, for water, we'll use 18 grams per mole as the molar mass. We can use a density of 1 gram per cubic centimeter. And then using Avogadro's number, right, I'm just going to write Na for Avogadro's number, and taking that all to the 1/3 power. So we get about 3 times 10 to the minus 8 centimeters as the average distance between water molecules. Or if we want to think of this in terms of angstrom, it's about 3 angstrom distance from molecule to molecule in water, which makes pretty good sense, because the volume of a water molecule, or the size of a water molecule, is about 3 angstrom. So now continuing along with this calculation for Kd, so I probably did not leave myself a good amount of room here. So I'll write Kd equals 4 pi. Let's see, where did my calculation go? I was like, which value of R are we going to use? That's not the gas phase R, that's the gas constant R. Okay, so we're going to use here 3 times 10 to the minus 8 centimeters. And then now using the diffusion coefficient of water, 2.3 times 10 to the minus 5 centimeters squared per second. And I suppose technically that's a centimeter per molecule, right? Like the average distance between each molecule. So now when we do that calculation, we get roughly 8.6 times 10 to the minus 12. That ends up being cubic centimeter per molecule per second. Or if we were to put that in our standard solution phase units, liters per mole, that's about 5.2 times 10 to the 9 liters per mole per second. So these numbers are fast. I know that minus 12 looks like it's really tiny, right? But converting that to liters per mole, 10 to the 9 inverse molarity per second, that's incredibly fast. Okay, so what if we use this equation to calculate that? Well, R, we know what that is. That's our gas constant, and we're going to use the 8.314 number. Temperature is temperature. And then now this eta right there, that is our viscosity, okay? Viscosity. So we could also use that in place of this equation and likely get similar results. Hopefully we get similar results. So standard units for viscosity are typically given in poise or even centipoise. So just for clarity, 10 poise is equal to 1 Pascal second. So that's like our preferred standard unit. But we typically see things reported in centipoise. So for example, 1 centipoise, so I'll say P for poise, that is equivalent to 1 millipascal per second, or 1 times 10 to the minus 3 Pascal per second. And for reference, water is just about that. So water is 1.002 millipascal per second, or we can just use roughly 1 centipoise for water. Now, so to keep this in our proper units, right, if we've used joule per mole here and we're using Pascal, I'll remind you that a Pascal is a joule per meter cubed. So that's going to be the correct unit to use here. So let's see, I'll box this off and note that this came from here. Okay, apologies for the sloppy board work. You guys know me by now. And then now we'll take this calculation down to here, and let's go for it, right? So we could also say KD is equal to 8 times 8.314 joule per mole per K. And then now that's all, then times 298K. And then now that's all divided by 3 times 1 centipoise, which is about 1 times 10 to the minus 3. That's going to go joule per meter cubed seconds. And then now when we calculate all of that, we get about 6.6 times 10 to the 6th. And that ends up being a meter cubed per mole per second. Or if we want to convert that into liters so we can be comparable, we get 6.6 times 10 to the 9th liter per mole second. So you can see we get just slightly different results, right? From using the diffusion coefficient and average separation of molecules, we get about 5.2, let's just call it 5 with 1 significant digit, times 10 to the 9th. But if we use the viscosity and with 1 significant digit, we get about 7 times 10 to the 9th. So the fact that those are both 10 to the 9th suggests that they're both in good agreement with each other. So we would really just kind of pick which calculation based on which type of data we had, right? If we only had data on the viscosity, then we'd want to use this equation. But if we only had data on the diffusion coefficient, then we'd use this equation. Both give pretty similar results. Okay, folks, I'll see you in the next video.